Hello, future listeners. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's the only way you can also help your friends explore my channel. And to keep me going, refreshed, and inspired, please don't forget to subscribe. This is the last example on three-moment equation. Quite challenging, but it would help you understand and master the concept on three-moment equations. By three-moment equations and analyze the continuous beam shown below by constructing the shear and moment diagrams. Also sketch the elastic curve. EI is 40,000 kilonewton meter square. Note that the support movement settlements. So we note that moment at A is 0 and moment at E is negative 30 times 2 or negative 60 kilonewton meter. So we then apply three-moment equations on spans A, B, C. So moment at A0 plus 2 times MB, quantity is 6 plus 7, plus moment at C times 7. The value of 6 area 1A over L1 for span AB, so we have to consider a strip. It is differential P is 25 dx, call that x. Therefore, it is integral from 0 to 4 of 25 dx. A is 2 plus x over L6, quantity 6 square minus quantity 2 plus x square. So integral 0 to 4 of quantity 25 dx, 2 plus x over 6, quantity 6 square minus 2 plus x, quantity square. While the value of 6 area 2b over L2, so we consider again a strip, then let's call that x there. X begins with this 0 load to that strip. So this load as to x equals 48 as to 6. 48 over 6 is 8. Therefore, the height of the density of this loading is 8x. And call this distance 6 minus x as our b. 6 length of load minus x. So differential p is 8x dx. So the value of 6 area 2b over L2 is integral from 0 to 6 of 8x dx times b 6 minus x all over L 7 quantity 7 square minus quantity 6 minus x square. Then equals reference horizontal line through B. So HA is above this horizontal line by 20 mm or 0.02 meter over L6. C is also above the horizontal line through B by 20 minus 12 or 8 mm, 0.008 over 7. So equals 6 times 40,000 quantity 0.002 over 6 plus 0.008 over 7. Simplifying, this integral is 3,200 over 3. This integral is 55008 over 35. And the value at the right side is 7520 over 7. So simplifying 26 MB plus 7 MC equals negative 1564.038. So call that equation 1. Then we have to apply three-moment equation on spans BCD. So moment B times 7 plus 2 times MC, quantity 7 plus 8 plus MD times 8. Then the value of 6 area 1A over L1 for span BC is integral of 8x dx. A is 1 plus x, so replace this by 1 plus x over 7, quantity 7 square minus 1 plus x square. Integral 0 to 6 of 8x dx, 1 plus x over 7, quantity 7 square minus 1 plus x square. Then the value of 6 area 2B over L2 for span CD is just PB over L, quantity L square minus B square, or 50 times 5 over 8, quantity 8 square minus 5 square. Then equals 6 times 40,000. So the line through C is, so B is below the line, horizontal line through C by 8 mm, so it is negative 0.008 over 7. D is also below by 13 mm or 0.013 meter, negative 0.013 over 8. So equals 6 times 40,000 times negative 0.008 over 7 plus negative 0.013 over 8. So the value of this integral is equal to 65952 over 35. This one is 4875 over 4, and the right side is negative 4650 over 7. So simplifying, 7 MB plus 30 MC plus 8 MD equals negative 3767.379. So let's call that equation 2. Then finally, for span CDE, make note that moment at E is negative 60. So we have moment C times 8 plus 2 times MD, quantity 8 plus 5. Then plus ME, which is negative 60 times 5. Then the value of 6 area 1A over L1 for span CD is 50 times 3 over 8, quantity 8 square minus 3 square. While the value of 6 area 2B over L2 for span DE is, we need to consider an intensity here. That's strip. Then let's call this X from the right. So that intensity of the load minus 20, imagine a horizontal line through this corner. So that would be intensity of load minus 20. Consider the triangle equals 30 minus 20 is 10 as to 3. Therefore, the intensity of this load, or the height of the strip, is 10 third x plus 20 as shown. So dP is quantity 10 third x plus t plus 20 dx. So that the value of 6 area 2B over L2 is integral of 10 thirds x plus 20 dx times B, which is x plus 2, all over L, which is 5, quantity 5 square minus x plus 2 square. So integral from 0 to 3 of 10 thirds x plus 20 dx times x plus 2 over 5, quantity 5 square minus x plus 2 square. Then equals 6 times 40,000. The horizontal line through D is this one. So HC is, C is above the horizontal line through D, 13 mm, so 0.013 rather over 8. E is also above the horizontal line through D by 10 mm, 25 minus 15, so plus 0.01 over 5. So equals 6 times 40,000, quantity 0.013 over 8 plus 0.01 over 5. So the value of this 601A over L1 is 4125 over 4. The value of the integral is 2658 over 5, and the value of the right side is 870. So simplifying, 8m sub c plus 26md equals negative 392.85. Equation 3. Solving these three equations simultaneously, we get mb equals negative 26.305 kilonewton meter. M sub c is negative 125.728 kilonewton meter, and MD is 23.576 kilonewton meter, which is positive. So having known these moments, let's now apply and solve for reactions and shears. So RA, RB, R sub C, R sub D, and R sub E. For moments, 26.305 for MB, 125.728 negative, so that's the direction. And for MD, which is positive, would be counterclockwise at the left of D, clockwise just to the right of D. So considering AB, summation moments about B equals 0 are 8 times 6 plus 26.305, then equals moment of the load 25 times 4 times 2. So from there we can solve RA equals 28.949 kilonewtons. Shear at B just to the left, this time we sum up moments then so that we can check the reactions together with the loads if they balance later. So summation moment A equals 0. Remember at B the shear just to the left is positive downward. So shear B downward, shear at B just to the left times 6. Then plus moment of the load 25 times 4, 2 plus 2, so moment arm is 4, 20 plus moment 26.305, then plus moment of the load 25 times 4 times 4 equals 0. So shear at B just to the left is negative 71.051 kilonewtons. Then consider BC. Shear at B just to the right is positive upward. So summation moment C equals 0. Shear at B just to the right times 7 plus 125.728 and equals 26.305 plus moment of the load 1/2 or 0.5 of 6 times 48 times 2. Moment arm is 2, 1/3 of 6. 0.5 times 6 times 48 times 2. So shear at B just to the right is equal to 26.940. So reaction at B, vertical reaction at B is shear at B just to the right minus shear at B just to the left. So 26.94 minus negative 71.051. So you simply add, consider that absolute value. So RB is 97.991 kilonewtons. Next, considering BC and we compute shear at C just to the left by taking moments about B. So remember positive, assume positive is downward. So shear at C just to the left times 7 plus 125.728 then plus 26, it's also, no, plus moment of the load, it's downward, 0.5 of 6 times 48, 4 plus 1, so 5, the moment arm, 0.5 times 6 times 48, moment arm is 5, 2/3 of 6, 4, then plus 1, then equals 26.305. So shear at C just to the left is negative 117.06 kilonewtons. Then next is shear at C just to the right. So consider CD. Shear at C just to the right is positive upward. So we sum up moments about D. Shear at C just to the right times 8. Then equals 125.728 plus 23.576 plus the moment of the load 50 times 5. So shear at C just to the right is equal to 49.913 kilonewtons. So from there we can solve R sub C, which is shear at C just to the right minus shear at C just to the left. So 49.913 plus 117.06 is equal to 166.973 kilonewtons. For the rest of the reactions, let's have it on the next slide. Next slide. So this was the beam, and these are the results up to R sub C. Then we have to apply moment at C and moment at D to continue. So Let's compute shear at D just to the left this time. Reactions. Shear at D just to the left, summation moment, consider CD. We sum up moments about C equals 0. So let's have moment equations this time. Then plus 50 times 3 and equals 23.576 plus 125.728. So shear at D just to the left is negative 0.087 kilonewtons. Then for shear at D just to the right, we consider DEF, summation moments about E equals 0. So shear at D just to the right times 5, then plus 23.576, then plus 30 times 2, then equals moment of the load. The load is divided into two, rectangular 20 kilonewton per meter and triangular intensity 10 kilonewtons per meter. For the rectangular, 20 times 3, 1.5 plus 2 is 3.5, the moment arm. So equals 20 times 3 times 3.5. Then for the triangular load, 1 half or 0.5 of 3 times 10, 30 minus 20 is 10. Moment arm is 2/3 of 3, 2 plus 2, so 4. So plus 0.5 of 3 times 10 times 4. Solving for shear at D just to the right, so it is equal to 37.285 kilonewtons. Now RD is 37.285 minus negative 0.087. So R sub D is 37.372 kilonewtons. Finally, RE can be solved by taking moments about D. So RE times 5 and equals, everything is clockwise, so 23.576 plus moment of uniform load 20 times 3 times 1.5 plus moment of the triangular load 0.5 or 1 half of 3 times 10 times 1/3 of 3, 1. 0.5 times 3 times 10 times 1 plus 30 times 7. So R sub E is equal to 67.715 kilonewtons. So we are now ready to sketch the shear diagram or construct the shear and moment diagrams. Let's apply first the reactions. 97.991 kilonewtons for RB, R sub C 166.973, RD equals 37.372, and RE is 67.715 kilonewtons. So for the construction of shear moment diagrams, let's have the graduation by 50s. So first, from shear force diagram, move up 28.949. Then constant up to here. Then minus 28.949 minus 25 times 4. It's going down. And the ordinate here is negative 71.051, which checks the shear just to the left of B. Then plus 97.991. So that's then constant. The value is 26.94, which is the shear just to the right of B. We checks here. And minus the area of this triangular load, 1 half of 6 times 48, from 0 slope to negative increasing. So second degree, this is negative 117.6. We checks shear at C just to the left, and negative 117.06. Then plus 166.973 is 49.913. This is the shear just to the right of C. We checks here. Then constant minus 50. 49.913 minus 50 is negative 0.087. The shear constant, and that's the shear just to the left of D, which is negative 0.087, plus RD 37.372, so that would be 37.285, minus the area of the trapezoid, 37.285 minus 1 half of quantity 30 plus 20 times 3. It is negative decreasing. So it looks like this, like that. So 37.285 minus 1 half of quantity 30 plus 20 times 3. The ordinate here is negative 37.715 constant. So therefore the shear at E just to the left is negative 37.715, though I did not compute it, but it's obvious because plus 67.715 reaction at E, we have positive 30 and constant, and minus the loading here, which is 30, so it is 0. So we will call this distance x1 before we solve x2 from this point to that point where shear is 0. Then this one as x3. Call that area 1, this one area 2, then x3 here, then area 3, and this one is area 4. Those are the areas that we shall compute. All the rest can be computed easily because they are just rectangles and triangles. So shear AB is 28.949 minus 25 times x1, and equate to 0. So 25 times x1, project above. So x1 is 1.1580 meter. Then for this x2 here, shear BC is 26.94 minus, so we have to consider strip height, call that x2, from zero load to any point. So intensity of the load as to x2 equals 48 over 6. 48 over 6 is 8. Therefore, the height is 8 times x2. So therefore, shear BC is 26.94 minus that area 1 half of x2 or 0.5 of x2 times 8 x2. Then we equate to 0 again to solve for x2, 0 shear at this intersection here. So x2 is 2.5952 meters. Then for x3, call that x3. Then intensity of the load. So this is 3 minus x3. Intensity of the load minus 20 as to 3 minus x3 equals 30 minus 20 is 10 as to 3. Therefore, the intensity of the load here in terms of x3 is 10/3 quantity 3 minus x3 plus 20. Therefore, shear in DE is 37.285 minus 1 half or 0.5 of quantity 30 plus 10 times 3 minus x3 over 3 plus 20. Then times x3 equals 0. So simplifying, shear DF is 37.285. So we have 30, 10 times 3 over 3, 10 plus 20 is 60, negative 0.5 of 60 is negative 30 times x3. So minus 30 x3. Then we also have negative 0.5 of 10 over 3 times negative x3, that's positive 5x3 over 3 times x3, so plus 5x3 square over 3. Therefore, shear DF is 37.285 minus 30x3 plus 5/3 x3 square over 3. Then we equate to 0 to solve for x3 where shear is 0. So x3 is, there are two values, one is absorbed, so this is the acceptable value, 1.3430 meters. Then let's evaluate area 1. Let's have this first plotting. So 0 from 0 moment at A plus 28.949 times 2, the area of this diagram. So that would be 57.898. Then plus the area of this triangle, which is 57.98 plus 1 half of x1, 1 half of 1.158 times 28.949. So it is positive decreasing, maximum at that point, and it is equal to 74.659. Next, for the ordinate here, negative increasing. So 74.659 minus the area here is 1 half of quantity 4 minus x1, 1.1580 close times 71.051. Again, 74.659 minus 1 half of quantity 4 minus x1, 4 minus 1.158 times negative 71.051, and it is equal to negative 26.304. Then 26.304 plus the area here, which is 26.94, so it rises, and the value is 0.636. Then we need to evaluate area 1. So area 1 is the integral of this shear BC, which is 26.94 minus 4x2 square from 0 to 6. So area 1, integral from 0 to 2.5952, rather, 0 to x2. Then shear equation for BC, 26.94 minus 4x2 square dx2. So area 1 is equal to 46.610 kilonewton meter. Area 2 is same integral, limits 2.5952 to 6, same shear equation, and area 2 is equal to negative 172.970 kilonewton meter. So let's continue plotting. 0.646 plus 46.610 positive decreasing is 47.246. 47.246 minus plus negative 172.97, so it is concave down. Negative increasing, so it is negative 125.724. So remember, negative 26.304 is the expected moment at B. Moment at B is negative 26.305, and this is negative 26.304, so that's very okay. Moment at C is negative 125.728, and this is negative 125.724. That's also very okay. Then plus 49.913 times 3, the area of this rectangle, so it rises to 24.015 plus the area of this rectangle, which is 5 times negative 0.087, so it drops a little to 23.580. The moment at D is 23.576, this is 23.580, so that's fine. Then plus area 3, so we need to derive shear equation for DA, which is equal to 37.285 minus area of trapezoid, 1 half of quantity 30 plus 10 minus x3 over 3 plus 20 times x3. So area 3 is integral from 0 to 1.343 of 37.285 minus 30x3 plus 5x3 square over 3 from shear DE equation dx3. So it is equal to 24.365 kilonewton meter. Then area 4, integral from 1.343 to 3 of same value, 37.285 minus 30x3 plus 5x3 square over 3 dx3, and it is equal to negative 32.510 kilonewton meter. So to continue, we have positive decreasing, 23.58 plus 24.365 is 47.945 minus 32.51. So negative increasing to 15.435 minus 37.715 times 2 goes down here, negative 59.995. Expected moment at E is negative 60, then that's fine. Then plus 30 times 2, so that's closest. So this is the moment diagram. Let's then project zero moments as points of inflections above and prepare the uh, elastic curve. So this will be the expected elastic curve. Note that it passes through or passes over the supports, the settled supports. So that's it for this problem. This is the last, and I hope that sketching the elastic curve and the constructing the shear moment diagrams is no longer a difficult job, because even if the loading is complicated, you have your high-tech calculator there for evaluating the area.